Welcome everyone to the Tartan planning series. We're excited to hear from Sebastian Scherer today. As an introduction, so Sebastian Scherer is an associate research professor at the Robotics Institute at Carnegie Mellon University, where he leads the AirLab. His research focuses on enabling robust autonomy in unstructured and cluttered environments. The AirLab's research spans all things robotics, including perception, localization, planning, and control. Some of the AirLab's recent achievements include winning the DARPA Sub-T Tunnel Circuit, an Outstanding Learning Paper Finalist Award at ICRA 2022 for their work on off-road driving, and the Howard Hughes Award for their work on full-size autonomous helicopters. Dr. Scherer received his BS in computer science, master's and PhD in robotics from CMU in 2004, 2007, and 2012. So I'll turn the time over to you.
Okay, ready. So today we'll give a bit of an overview of some of the planning work that's been going on in the lab, and I'd encourage you to really look at how do the papers in more detail if you're interested. But I want to kind of put this work a little bit into context with the basics. So we'll start going more over the basics. So like Brady said, we do all kinds of things related to robotics, but today we'll kind of really dive into the planning, and I'll not give a big introduction on why, but I think you've seen a lot of this already. So let's start with a little bit of an intro. So sorry if I scared you right away with some equations, but the idea is this is really just the high-level concept, right? So you can think about the planning problem on a very abstract level. We want to come up with some trajectory. There's some objective function that we want to optimize, and there are some boundary value constraints. We have maybe some non-holonomic constraints, some system limitations, and maybe some limitations given to us based on the cost function. And so, this is a variant of the optimal control problem, where you're really not necessarily looking at coming up with the controls, maybe just trying to come up with a reference trajectory. So what does that mean in practice? So for example, non-holonomic constraints might be the turning limitations of the system, or it could be things like yaw rate limits. And then for the cost function, there's many different cost functions we'll look at today, but these are the things you typically think of, maybe shortest time to completion, but it could also be things like don't fly through something. One cost function we often look at our obstacles, and that is one way to do that is with time to collision. So you can say, okay, how many times does it take me to hit this obstacle? And so you can imagine that these types of functions can sometimes be expensive to compute. So now that we have this problem, these are all continuous functions. Like how do we solve this problem? And so the way we typically go about this is we discretize this problem. And the reason is that we have limited time. We want to do this in real time. And we're on a computer, so we don't have an analog computer anymore. So if you think about it, one more level removed, we can abstract this problem as a graph, right? So we're picking a set of choices, left, right, and then you're trying to search through that graph to find the best set of actions. And so this graph can be constructed implicitly, explicitly, and so that's where a lot of the planning research comes in. And so to think about how do we define an edge, and that's typically due to how our system model, like how do we go from one state to the next. And then we have objective functions like the ones I just showed on time to collision or other things where we're trying to see, okay, how expensive is an edge to construct. And so one of the challenges that you often have is, okay, let's say you want to create this graph, where should you put your graph? What resolution should you pick? How many edges? And so that's where sampling-based planning comes in, right? Where you can say, okay, I have this problem. I'm not going to pick these vertices ahead of time in a fixed structure, fixed lattice. I'm going to construct this graph on the fly. And so you add an edge to the based on your sample and keep expanding. And I'm glossing over some details here on how to rewire and all these things, but high level ideas, constructing this graph on the fly based on where you think samples are valuable. So that gives you a new new way to construct this graph, right? And so that's where a lot of planning for us in terms of a time budget comes in, is where do you want to put those samples? Where do you construct these edges? Which edges do you evaluate? And so we'll go through some examples of this type of work in action. I'll go relatively fast over this, but I just want you to get a flavor for some of the things that are happening. So in the informative path planning problem that we've been looking at, the idea is to maximize the information that you gather in an area while you have respecting the budget constraints. So here in this video, the red is information that you can gather, and you're trying to find a path that maximizes that information that you gather. And as you can see in animation already, there is a tree that we are constructing. Okay, what can we do in informative path planning? This is actually a very common problem. So there are many uses for this, and I'm not going to go through this whole list, but you can imagine anytime you have to gather data in an optimal way, or you're searching for something, this is a very relevant problem. So again, like we went through before, there's many ways you could try and construct this graph. So you could try and come up with a fixed graph that you're essentially searching over. You could do it more in a one-step plan where you're just looking at the objective function going, okay, what is the next thing? Or you can try and construct this kind of graph. And so in this work, we're taking more of a tree approach. And so the key idea with this tree construction is really being smart about where you put the samples and then estimating what is the cost of an edge, because an edge is typically expensive to compute, right? So in this example here, we're trying to figure out, okay, how much information did we scoop up over this region? And so you can imagine that that is an expensive calculation. And then sampling efficiently allows us to get large plans over these big areas that we have to plan over in a fast way that we can do in onboard compute, right? And so a lot of the problems you'll see today are really, we have a deadline for our planning, so we can't really wait a long time to compute the optimal solution. In terms of the algorithm, it's actually, it's very similar to a regular RT algorithm or RT style algorithm, but it's really about the sampling and the reward calculation. And so the reward is based on minimizing entropy. And then you can see that, as we slide this camera over the terrain, we basically have to figure out, okay, how much do we reduce the entropy? And so we can approximate that edge reward to really speed up the calculation. I'm not going to go into details on this. I'll ask Brady later. And then so if we run this over a large set of experiments, this system performs better than a baseline algorithm that's kind of in a similar way. Now, since we don't want to only plan once, one of the things to think about is how do we do this efficiently? And so one of the tricks we use here is to not reconstruct that tree every time. We're basically recycling the tree. And then we can efficiently replan. And so this is also, and we want to replan because the execution of a plan is not always perfect, right? We might have predicted that we scoop up some information somewhere, there was something we missed, so we have to replan to do that again. And so you can see the tree displayed here in this with all these circles, and that's due to there's some motion constraints on the vehicle that it can't turn in place, and so the edges are not just straight lines, but they're basically these different paths. Okay, and then so we want to also test this on real systems, and so we've also had some experiments trying to find fires, for example, at one of our test sites while we're doing tree recycling both in the air and on the ground. So the next question is, sometimes we're interested in not just static things like maybe a fire that's sitting on the ground, but we might be looking for people or other things. And so the world is not static, and so keeps evolving. And so this so we need to be able to plan on this evolving information and also represent it. And so one way to represent this is, for example, as a particle filter. If you have a lot of uncertainty, if you had less, you could use a Kalman filter. But now you can imagine that if you have that evolving information, it becomes expensive, even more expensive to predict what's going to happen. And so here we developed a Monte Carlo tree search algorithm to predict what the value of the long horizon plans is, and then search, and using that Monte Carlo tree search allows us to essentially get a better breadth of the decisions while still having a good terminal value prediction. Okay, so this was kind of the high-level idea on the informative path planning, and you can see already that trying to predict this, what is the value of the future of my decisions is valuable, right? And so that's kind of where this also connects to the next topic on exploration, right? So for exploration, you have a similar problem where you're saying, okay, I might want to go to 3 different future places where I can explore the space, but I don't necessarily know which space is more valuable. So similar to Monte Carlo tree search, in this case, we were just searching before further out and using that to estimate the value. Here, we're actually using actual runs on the robot to learn what the value of those states are. And so the input there is to say, okay, we have some projected map of that future location and image, and then we're trying to predict the value function of what that value is. Now, since those runs were done before, it's difficult to ensure that you have covered every possible situation. And so online during execution, the network essentially is adapts, because as it makes decisions, it will see how much it gained and then can refine its network. So this was tested on a drone inside a corridor environment and evaluated on data sets from a lot of different experiments. So one of the metrics we use to evaluate how good the system performs is regret. And so you can see here there's 2 potential goal points the robot has. And so if it would pick one that already has a lot explored space, is low value. If there's still a lot to see, it should be higher value. And so you can see here on a data replay the robot will pick different potential goal points, and then we can evaluate if our system picks the right goal points, right? So here, the red value is higher value because it's much less seen space, while the blue one is in an area that has already been seen. So the sampling is done on frontier. So we extract frontier points, and there are lots of frontier points. It picks a subset of these frontier points.
So the input is just pure RGB image.
No, it's an overhead map and an image.
Do we have to find any semantic information?
So in some sense, the images are somewhat semantic, right? I mean, it is going through a network. Okay, so let's keep going. So so we evaluated this on a bunch of different data sets that were previously collected, and we compared this to the existing method that does not use that value prediction. And then also tested this on actual robot experiments. And here's just a small snapshot where you can see, okay, it does pick some higher value places instead of the previous method. Sometimes would skip these potential places where it would find better information. And so compared to a previous approach, the system is able to get better coverage. Okay, let's see. So next, we're kind of going to switch gear from a lot of information gathering to completely 180. So the problem we're looking at here is how do we plan for aircraft that are flying in airspace with other aircraft? So we'll have autonomous aircraft together with regular aircraft. And in the robotics literature, you call that problem social navigation. And so we are essentially cooperatively interacting with other human agents to jointly safely navigate in that airspace. And so so there's one of the challenges here is that we don't have that reward function. And I think you're kind of starting to see a little bit of a theme in this work, is that there's in a lot of our problems, it's hard for us to define what reward really means and what the cost is. And so the way we solve that problem is to use historical data to learn how humans balance performance with safety while navigating. And so we have done a lot of data collection at 2 different airports, on untowered and a towered airport, and we also have some kind of online streams that we're getting. And so we have data that includes ADS-B, radio, and the weather, and so we can use that to make these decisions. And so, but there are really kind of 2 main factors that come into play here is we want to fly with these other agents, but there are also some guidelines that humans are expected to follow that we want our autonomous agent to also respect. And so that's the first thing we'll talk about, and then we'll talk about how to incorporate the other agents. So we have all this data, great. So we just need to throw our algorithm at it. But I think that that's not the whole problem, because we don't have enough. We'll never have enough data to encode all those FAA guidelines, right? So you can think about a driving example where if the traffic light's red, you should not go across the road. But you might have seen somebody drive over a red light, or you might have seen people stop various ways, or they don't follow the rules necessarily. And so how do we incorporate this? And so the idea is to merge signal temporal logic with this imitation learning to try to enforce enforce these rules and get a good behavior. So for example, we have this in flying, you have this rule, okay, first you have a downwind, base, and final, and you don't want to overfly. And so you can turn this into an STL specification, and then we add that to the system. So this, you can think about these rules essentially like a racetrack around the airport. And so the way we do this is to essentially add STL as a constraint in this MCTS search, and to try and and then also learn from the data in the MCTS to match the behavior. And so you can see once we do that, we if you incorporate this, we'll see that it basically does a good pattern and follows the expectation better. If you don't incorporate that data, this agent might, for example, shortcut because it's a least distance, but maybe doesn't necessarily follow the conventions. And so if you look at more of a quantitative analysis, we can see that with incorporating STL and this goal network, we get the highest success rate, but also the highest score in terms of matching the STL constraints. So one of the things to notice is that the STL logic here is not a hard constraint that keeps that the robots have to be inside, but it's a guideline that people are supposed to follow. Now, once we have an agent that can follow the FAA guidelines, the next question is how do we add behavior with the other agents? And so this is a cooperative game where we jointly essentially optimizing to not hit each other and get to our goal. And so this is work together with Gino. And so we again have this Monte Carlo tree search, but instead of just us planning where to go, we essentially have to plan for the other agents as well. And so we have these various modules that basically trying to predict the path, as well as the reference module that tells us, okay, where do we need to go to behave well, and they interact in that search while we roll out the policy. And so we performed experiments with human pilots against comparing a regular pilot, our algorithm, and a baseline algorithm to see, are there some discernible differences and how does our system perform? And we have to do this type of study because it's really hard to define what is good behavior in this type of system. And so we recorded a trajectory and asked them a question here after that. And so on the high level, our method was comparable to human performance and also was safe. We also had some other things in there, if they could distinguish the human from the other algorithms, but that was not a good question because people think that an algorithm that flies well is a human. So, okay, cool. So in the final, we'll kind of go from high in the air back to the ground, onto the ground. So no more flying. And so here really you can think about this problem of how do we solve the last 10%, right? Like we have pretty good algorithms for nominal problems, but there's all kinds of corner cases that require a lot of engineering, to fine tune and so on. And it's easier for somebody, a designer, to show examples, but it's difficult to manually abstract that approach. And so, another way to look at it is we want the engineer to be on the loop instead of in the loop, right? Yeah. And so we'll go over one example of how we've been looking at this in the problem of off-road driving. Now, before go there, I just want to give a little context for relationship between reinforcement learning and planning, because that's sometimes a little hard. People have some hard time keeping that apart. So, for reinforcement learning, you have a policy, you have some reward signal, you might have a model, and you have a value function, right? And so for model-free reinforcement learning, you're essentially trying to build a direct mapping from state to action. For the case that we look at, we typically have a model, so meaning we can go, we know how we go from one state to the next. And then you can think about this value function like an endgame database for some planning things, or a heuristic. And the reward function, we also sometimes call a cost function, right? So just kind of make that relationship here. And so what we'll really look at here is how do we learn that reward signal, given that we have a model for how the robot behaves, and we have some way to plan on this. So estimating where to drive is difficult, right? If you would, a standard way to do this would be to say, okay, we'll do semantic segmentation. We'll say, okay, grass, trail, or something like this, but it's an arbitrary class, right? So here we have some traversable vegetation. This one we can't drive over. Similarly for the trail, here's a hole, there's a good trail. And so how do we do this? And so, like I said before, the traditional way would be to have an engineer with, maybe a panel like this, doing, fine tuning for weeks on trying to figure out what that function should look like. And so what we want to do instead is, use examples from human to learn how to drive, right? And so it's pretty easy to have somebody drive around, give good examples, and see and be able to take them. And so the data collection is really just driving around, and depending on how often you've driven somewhere, kind of defines how good something is. And so one other thing that is kind of interesting here is that we want to have a sense of when the system is uncertain about something and not certain about something, right? So we take our point cloud, we create some features, and then create a set of different cost maps based on these features. And the way we do this is by looking at how often did an expert visit a state versus our learner visit a state, and feed that back to as a signal to learn this cost map via and so we calculate this ensemble of cost map, and that gives us an idea of what the uncertainty is, and so we can calculate a risk-aware cost map that's then used for during test time. And so, for example, with that set of cost maps, we can calculate this conditional value at risk, and that gives us essentially a knob to figure out how risky we want to be. And so if you look at this example result here, we, as we sweep over this value of conditional value at risk, you can see that the trail stays pretty consistent. So it has very little uncertainty about what a trail is. But in some of the other areas, the value changes a lot depending on how risk averse you are. So when we put this all together, we can then drive autonomously on these on trails, for example, and also figure out, should drive not, and depending on risk of we can adjust our risk portfolio. So this using this method leads to better reconstruction of the expert path, and then in the overall system also less interventions in practice. So overall, this learning from a demonstration type of framework does work good and helps us really cut down this tweaking of features, because we don't necessarily know what is better and what is worse, and these values are sometimes very sensitive. So to summarize, I wanted to just give you a quick introduction on putting some of this planning work in context, how we can use this for informative path planning, and then talk about how this reward function learning in a couple of different ways. And then we talked about learning from expert demonstration to enable safe navigation for off-road driving. And so I went a little fast on purpose so that I can leave a lot of time for questions.
Okay, thank you. Let's see if this is working. We switched over to it now. We have a lot of people here in person too. But yeah, if there are any questions, you can raise your hand on Zoom, enter it in the chat, or if you're on YouTube, you can also enter in the chat, or if you're a person, we're happy to take questions. So, Mitch, go ahead, Mitch.
I had a question about the last part about the inverse reinforcement learning. We were talking about the features that a graduate student might be like changing. So when you're doing the imitation learning at the end, you're trying to learn those feature values, not necessarily match the state action. Like the loss function on that problem is about the feature values.
So
it's roll it out.
no, so it's trying to match the state visitation frequencies, and the feature maps are fixed, and just learning the weight vector.
Yeah, so we do have one question on the Q&A. Said, can you please elaborate on the information gathering for dynamic object tracking scenario?
So for the dynamic object tracking, so we have a set of, so the problem is we have a set of dynamic objects we're trying to find. Those dynamic objects, if we see them, we reduce the uncertainty. If we lose them, it will spread out. And so, so we're trying to, and so that's basically the planning scenario.
I have another question.
Sure.
At the beginning, you motivated that we want to discretize our states and then form this discrete graph. Why can't we do planning in a continuous dimension?
So, I mean, you can think about even trajectory optimization as a discrete problem, right? I mean, we're just in a just a discrete space, right? So, I mean, let's say you're doing some kind of trajectory optimization. You'd calculate on the trajectory, you might calculate the gradient or something like this, and then you're calculating the next iteration, right? So you could think about this as adding to your graph. So now you have, your graph has basically these two lines going down. There's no connections in searching in between, but you have, so in some sense, you always have to discretize in a discrete computer. even if you're optimizing a continuous function. Yeah, I mean, that will maybe change with quantum computing, or if you go back to the old times.
Could you tell me some like possible future direction for the social navigation work?
Future direction for the social navigation work? Yes, so so in the current work, we only looked at homogeneous agents, so planes of similar sizes flying, and so one future extension is how do we do this for heterogeneous agents, and then also in situations where you have some communication between the agents, so they can share intent. So it's not just you're trying to infer intent and you have a sense of what's happening, but some sharing of intent. This could be like formation flying, for example. And then the other part we kind of glossed over is that even if you have that type of system, you need another level to really guarantee the safety of this if you're going to execute it. So that's next extension.
Okay. Well, by heterogeneous agents, you mean like multiple types of UAVs? Or like,
Yeah, so you could have different sizes of UAVs, and you could have different types of flying manned aircraft. You could have a helicopter, you could have some fixed wing. There's types of aircraft.
Yes, we have one question from Zoom saying, could you elaborate on the regret metric for informed planning?
Yep. Let's go back. Let's see. Here we go. So the regrets, and Yafi, you can correct me if I'm wrong, but the regret here is basically how much of a if you make the wrong decision, what is the difference between that and the best decision, right? So your decision versus the best decision, what is the difference between that, right? Yeah. Okay, so for the social navigation, did we do any experimental tests? So we did experiments and simulations. So that was that user study. Basically, we had more than 20 pilots fly in simulation with our system, and then we evaluated the performance. We have not done any real world test yet, but that is hopefully coming soon.
I have one question too. I guess like what technological advances are you excited about that you think can be leveraged well within the planning space?
Okay, very broad question. So I think the combination of learning and planning is definitely an exciting direction in general, because it helps us leverage things and learn. I mean, learning the reward functions for sure, but even in the algorithms themselves, often it's difficult to design these trade-offs for real-time algorithms. Like, where do you search, which decisions do you make, and you just look at the profile essentially of your missions and what a best solution would look like. You could learn some things. So I think that's something that's exciting. And then even on we did not really talk much about essentially the model part of planning, like how do we go from one vertex to the next. But there's also a question about what is the model. Sometimes there's a lot of uncertainty. For example, for off-road driving, you might not really know, are you going to arrive up after an action? But typically we design these systems so that we don't have a lot of execution uncertainty too, because then it would increase the problem even more. But Yeah.
Okay, we can go to this question. There's another one about regret while we're on the slide. It says, do we see any benefit of using the regret metric as compared to the information gain metric? Are they complements to each other?
So the regret is really on the predicted value of that state, essentially, while right, so the regret is relative to the other states, while the information gain is just an absolute metric. So so I think it's a little. Sometimes I think it's a better metric to decide, is a relative decision better at that point. So I think that would make it a little more attractive of a metric. But I mean, we always want a bunch of metrics and then kind of see what are the characteristics of something.
Okay, and then we have another one that says, follow up on the previous question. Can you use information gathering to reduce the uncertainty in the state estimation of dynamic objects?
Yes, so that's essentially what's happening in that search for dynamic objects. So I can go back there and then a little fast. So if you look here, you see those particles kind of dispersing. But then once we actually make observations, then we can observe the state of these ships again. So anytime we don't see them, they disperse. Once we start seeing them again, they'll reduce that uncertainty.
So this crash is actually.
Oh, right. Yeah, that's the sum of the variance. Yes. Yeah.
Nikhil?
So I have a question regarding social navigation. Have you guys considered using language models to kind of encode guidelines and then use those features to do your planning, or like language models that cannot do that level of, because like right now they do a very good job embedding text. So have you actually considered that direction?
Not yet, but I think it is an idea. I could almost see it more on the STL side, where you'd use this to potentially set a set of constraints or plan, essentially. Like if you get some instructions, especially on the radio, and that for sure can add constraints. I think that could be good features to then learn on, for example. I mean, I think the large language models so far are haven't really been trained for, like spatial type of navigation as much. So I think there's probably more work to be done there.
Would be an interesting application.
Yeah.
Thank you.
So we do have one question in the chat. It says, how do we bake more adaptive behaviors into information gathering? What is Professor Scherer's take on going beyond simply covering the space?
Right. I mean, I think there's the objective function for information gathering is hard to define, I think. So, I think for example, in the example video we just looked at, we want to keep track. Our real objective function is we want to keep track of these ships. We want to find them and keep track of them. And so we make up a function that we think represents that. And then we call it, I don't know, entropy. Right? So it's, and so that's a function that we're then actually optimizing. So I think the actual objective function itself is a tricky thing. And then the second part of this is we have, in this case of keeping track of ships, we have multiple behaviors we want, right? We want to have a search behavior of looking for ships, but then also of the tracking behavior to localize the ships better. And so that is definitely something that is interesting, and it's a hard trade-off that you have to make that depends really on your user as well. Like would you rather see more ships, or would you rather know where those ships are better, for example?
Okay, we'll do this one from the chat again. So a follow-up question. Shall we treat information gathering as a multi-objective planning problem, namely balancing exploration and task performance?
Yeah, I mean, it is a multi-objective planning problem, for sure. But it's also, so it's not just a couple of objectives and you're trying to find a Pareto front. It can even be like a sequence of objectives as well. But yeah, it is, yeah, not a single objective function for sure.
Yeah, the question was about like more general, like your stance on like planning in general. And like planning is a very broad area, and most of the work we are doing right now is to combine some sort of learning plus planning. What's your like future vision of our lab's direction regarding combining very large deep learning models or large language models along with our traditional approaches?
Sure. Yeah. I mean, I think on the high level, so I think you want to have the ability to have reasoning in your system, right? So you can use, maybe to kind of contrast this, right? I mean, we could also say, okay, why aren't we just doing Q learning, right? Basically end-to-end, Q learning. And so I think the part of the reason is that you want to be able to trade off different choices, right? So you could go left or you could go right, and having some planning, some kind of tree, it could be MCTS, it could be some RT, it could be some trajectory optimization, right? Having some kind of reasoning in there allows you to make better decisions compared to something where you essentially have to hard code that state action kind of pair, right? And so that is, I think, where you can get a lot of value. Now, once you have done that reasoning, there's nothing stopping you from essentially learning shortcuts, right? Like, so now if you've done more reasoning and you're saying, okay, now I can go, I know that going from this state to that action is a good idea. You can try and encode that into some policy that's easy, right? But if you have higher level decision making, I think it's useful to have some reasoning. So I mean, this is kind of planning in a very broad sense, right? But I think that's roughly, I think, the high level of philosophy.
Okay, looks like we can do one last question. But we have a couple, I guess. We want to finish. How much do you rely on offline data and simulations versus real-time online data?
So offline, do we use any simulated data? What I showed? I don't think so. No, it's all real data. Yeah. Makes the answer easy.
Okay, I think we'll close with that. Thank you everyone for coming. And we have a couple sessions left that we're excited about. And thank you, Basti, for this great presentation.